Hey everyone! Okay, tonight we're going to start on chapter 6. The second half we're going to cover earthquakes. So what is an earthquake? In very general terms, an earthquake is just a vibration of the earth caused by a sudden release of energy. This is caused by movement of one block of rock slipping past another along fractures in the earth's crust called faults. These occur along all three types of tectonic plate boundaries: your divergent boundaries, your convergent boundaries, and your transform plate boundaries. Destructive earthquakes can cause structural damage to buildings and infrastructure, changes in water level, landscape, and loss of life. Earthquakes are also the origination and cause of the tsunamis that can devastate coastlines. Earthquakes that occur far out at sea have a significant impact on the movement of ocean water. So what causes an earthquake? What happens is you've got an original position of rocks, as seen up top here, and then a movement of a tectonic plate causes the rocks to start to bend, and as they bend, they start to store potential energy. And the higher the friction between the blocks of rock, the longer it takes for them to slip past one another, and the greater that stored energy becomes. So once the strength of the rock is exceeded, the slippage actually occurs along the fault line. So the slippage, you have all this friction, and it builds up until finally they break apart. If you have lower friction between the rock units, it doesn't build up as much stored energy because they're able to slide past each other much easier. And then finally, the rocks cease to be bent because of the plate tectonic energy and return to their original shape, but they are in a new location. This slippage can occur in cycles over time, which gives us an idea of when a future earthquake could be expected along a fault line. However, it is important to note that it is not possible to predict earthquakes. We can just guess at when we should expect another one. Most earthquakes occur at tectonic plate boundaries, and the deepest earthquakes occur in subduction zones. So if you remember back to chapter 5, we talked about plate boundaries. You see the highest concentration of earthquakes, the ones with the deepest ones, occur along the western coast of South America. You've got them along the Aleutian Islands, along the eastern border of Russia, and along Japan. These are all subduction zones. So what happens at these zones? So if you remember, as you have an oceanic plate or oceanic crust subducting under a continental crust or another oceanic, as it slides under another plate, they're still pushing up against one another. There's still a lot of friction there, which causes a significant number of earthquakes as they pass by one another. But as it subducts into the asthenosphere, you've still got friction occurring. You've still got that energy going on. So there are earthquakes that do occur along that subducting plate at depth that can be reported at the Earth's surface. Now, earthquakes release their energy in waves. And when we discuss the energy waves of earthquakes, we need to understand the amplitude and frequency and the difference between these two terms. So amplitude is the maximum change in an energy condition over or under an equilibrium position. So this line here is our equilibrium position, where nothing is acting on us or our rocks. We're just hanging out. If something starts to act on us, then we start to shift in our energy condition above and below, because any sort of action has an equal and opposite reaction, right? So if we have an energy forcing us up, it's going to bring us back down. So the amplitude is how far above or below, or to the left or to the right of our equilibrium point we are. Frequency, or wavelength, is the distance between successive high or low peaks. So the distance between one high peak to the next, or the distance between one low peak to the next. So what has changed between graphs A and B? Well, our wavelength has become much shorter between graph A and B, right? But our amplitude has actually increased. And then in C, our wavelength has become much longer and our amplitude has decreased. So now let's talk about what an earthquake is in greater detail. Earthquakes release stored up energy as seismic waves. which travel through the Earth's interior and along the surface in all directions from the focus or hypocenter of the earthquake. So the hypocenter is where the earthquake actually originates within the Earth's crust. The point on the Earth's surface directly above the hypocenter is known as the epicenter of the earthquake. So the epicenter isn't actually where the earthquake occurs. The earthquake occurs at the point called the hypocenter. Seismic waves are elastic energy that is caused by the sudden movement of rock or by an explosion. They are measured by an instrument called a seismograph or seismometer. If you remember last week we talked, there are two types of seismic waves. There are body waves and there are surface waves. So the body waves travel through the lithosphere and the entire interior of the Earth. And like we said last week, they are broken down into two groups, the P waves, otherwise known as the primary waves. This causes the ground to be compressed and expanded in the direction the wave travels in a push-pull motion. So like you pushed a spring and then you release it on the side. You pushed the spring and you release it on the side. These are always the first seismic waves to arrive at a seismograph station. Your S waves are your secondary body waves. These cause the ground to move up and down along the direction the wave travels. So like a sine or a cosine graph. The second seismic waves, or they're the second to arrive at a seismograph station, but liquids and gas do not transmit S waves in this up and down motion. Only solids can. So like we talked about last week, that means once you get to a certain distance away from your epicenter, you will actually not get an arrival of any S waves because to reach your monitoring station, it would have to pass through the liquid core, and at that point the wave can no longer propagate. The next group are surface waves. These are waves that travel along the surface of the crust and not through the Earth. They have higher amplitudes and their vibrations last longer than body waves. As a result, they often cause more destruction. So if you remember last week, we saw that the S waves occurred second, but then usually shortly thereafter we had our surface waves, and they had a much higher amplitude than our S waves. The two types of surface waves are Rayleigh waves. These cause the ground to roll like an ocean wave in the direction the seismic wave travels. Or Love waves. These cause the ground to move side to side along the direction of the seismic waves travel. So here we've got our seismic wave moving from left to right, and so we've got this rolling motion of the Earth's surface. Here we've got it moving left to right, and as it moves, it's pushing the material perpendicularly side to side. So how do we locate the source of an earthquake? So geophysicists have created a model of the Earth's layers and use this to determine their composition and the speed at which seismic waves travel through the various layers. From this model, a seismic travel time graph is constructed. A seismograph station determines the time interval between the arrival of the first P wave and the first S wave at their location. Once this information is received, a circle with the radius using the distance indicated on the travel time graph is plotted on a map. The earthquake could have occurred anywhere along the circumference of the circle. So how do we determine the direction to the epicenter? Okay, so if you have your reading station, and you have your P waves arrive, and then your S waves arrive. Here's our point, and say we had 2 minutes between them, and we know that these waves travel like 450 miles a minute. So we draw a circle around this with a radius of 500 miles away. So it could occur anywhere along that radius. We have to figure out where along there it occurs. So what we need are at least 3 stations to record and allow us to triangulate the location of the epicenter. So when the circles of the travel time distance intersect, this gives you the location of the epicenter of your earthquake. Sorry. So like we saw last week, we have our P waves, and we have the arrival of our S waves. We're able to use that, and we graph it on a travel time graph. So here the example is a 5-minute time interval from when the P wave arrived to the S wave. Here's our 5-minute interval section. Okay, and so we know that at our 5-minute travel interval, it's approximately 2,000 miles or 3,500 kilometers away from the actual origination of the earthquake. So then, the seismograph station determines the time interval between the arrival of the first P wave and the first S wave and plots it on their time travel graph. So here we've got our seismograph station A with a 5-minute travel time, 3,500 kilometer distance. Really sorry, guys. Seismograph station B has a travel time of 7 minutes, which is 4,900 kilometers from the distance, or a 4,900 kilometer distance. And then C has a travel time of 10.5 minutes, giving us 8,200 kilometer distance from station C. So now what do we do with this information? So now we pinpoint our seismograph station A and draw the radius. And then we pinpoint B and draw the radius. And pinpoint C and draw the radius. And all of these intersect right here. So this would be our earthquake epicenter. So this is the point on the Earth's surface below which the earthquake occurred. Right? So the earthquake didn't occur right at this point on the surface. It occurred somewhere below this point in the Earth's interior. Earthquake size and strength is measured in 2 ways. The first way is measured on intensity. This is based on subjective observations of damage or earth movement using the Mercalli scale for a reference. The Mercalli scale uses Roman numerals. And so table 6.1 in your book breaks it down. So a 1 would be not felt except for by a very few. 4 would be during the day, felt indoors by many, outdoors by a few. Kind of like a heavy truck hitting a building. A 6 would be felt by all, heavy furniture moved, and in older buildings you get damage to the buildings. The highest on their Mercalli scale is a 12. This is total damage. The waves are actually physically seen on the ground. Objects are thrown upward. Significant loss of life occurs with this one. The second is magnitude. This is based on an estimate of the energy released using the seismograph records. This is used based on the Richter scale, which I'm sure many of you have heard of at this point. This is where each level of the earthquake causes 10 times greater ground motion over the level below it. So here we have the Richter scale. So a magnitude of 1 is generally not felt by humans, but could be recorded by some very sensitive equipment. A 2, very minor earthquakes. A 3 is 1,000 times greater than the one, sorry, 3 is 1,000 times greater than a 1 or a 0. And these are minor earthquakes, very light earthquakes. So when we talk about magnitude 4 to 5, these are the ones that we most commonly hear about. These are light earthquakes with shaking of items indoor, some minor property damage. In 2011, there was one in Arkansas that was a magnitude 4.7. Between 5 and 6, there was one in Virginia in 2011 that was a 5.8. 1994 in New York was a 5.8. So as we start to get up, if you start looking, you see that these higher magnitude earthquakes tend to occur at transform or subduction zones. We've got California, Japan, Charleston, South Carolina is actually not at a subduction zone, but Turkey, Mexico City, Japan, Alaska, Chile, these are all areas with subduction zones. It's also important to note that it does not accurately measure the magnitude of very strong earthquakes above a value of 8. Hiroshima atomic bomb was the equivalent to 15 million kilograms of explosives. So just for reference, that's right about a 5, 4.8 or 5 on the Richter scale. So that kind of gives you a mental comparison for how much energy these higher level earthquakes had. So this is a comparison of the modified Mercalli, the Richter, and the moment magnitude scales. So the moment magnitude, does not correlate directly to the Richter scale. and it's not typically used. But here's a comparison of how much dynamite energy, or how much dynamite you would have to use to create the same amount of energy for these. The Asia-Pacific region is the world's most disaster-prone, with earthquakes and floods wreaking havoc on economies. So why do you think this is? So like I pointed out, those are all areas with subduction zones, a lot of different plate boundaries there. It's a large area of the world with very long coastlines. Coastlines tend to sustain more damage. More tectonically active zones, more faults in the regions. This large area is also subject to a monsoon climate and typhoon occurrences. Higher population density, numerous large cities, and large areas that are underdeveloped and lacking means to really build against these common natural disasters. So factors which determine the degree of earthquake and associated destruction include the magnitude, the duration, the actual nature of the rock and soil in the area. So if you have very competent rock under your building, you're not going to have as much impact or damage as if you were on a very loose or sandy soil. Proximity to populated areas, the more buildings there are, the more fall hazards and damage hazards there are. Susceptibility to earthquake shaking, proximity to coastlines, and proximity to mountain ranges. So destruction associated with earthquakes is caused by the shaking of the land and structures by the seismic waves. And an earthquake can actually cause a liquefaction of saturated soils, in which soils that already contain a significant amount of water. During an earthquake, the vibrations can actually cause it to move as a fluid. Another destruction are fires due to the breaking and igniting of gas pipelines, lack of water due to breaking of water mains, inland flooding due to damage or destruction of dams, coastal flooding caused by tsunamis caused by offshore earthquakes, landslides in mountainous areas, and ground subsidence. This is where as the earthquake comes through, it actually causes subsurface cave-ins or dewatering of aquifers and can cause the ground to collapse. So most earthquake damage is caused by the shaking as seismic waves travel through an area close to the epicenter. So this just shows the destruction of a building from the physical shaking motion. Damage due to soil liquefaction. This is where the buildings are not shaken apart, but they have sunk into the ground or fallen over. So this, like I said, when you have your saturated soil, the soil grains end up floating within the water, acting as a fluid as a result. And so because of this, your soil is no longer providing any sort of support. It is liquid. It takes the shape of whatever's around it. So it's not holding up your building anymore. Your building sinks right into it. So this is actually tilted buildings that are on top of unconsolidated sediment that liquefied or acted like quicksand during a 1964 Japanese earthquake. So you can see the buildings are still fairly intact. They just sunk or fell over because of the reduced cohesion of the soil. I'll post the link to this. This is just a liquefaction demonstration. And another one, and another one. So this is an example of destruction due to fires, where the buildings were not as heavily impacted, but gas lines or pipelines were damaged. Okay, this one there's not as much structural damage, but gas lines could have been ruptured, causing fires. This you have significant physical damage and the ignition of flammable materials, the lack of availability of water to prevent the fires. And many dams around the world exist in mountainous tectonically active areas. So these are two dams that were damaged in the Taiwan earthquake in 1999. Okay, so we talked about coastlines being susceptible to tsunamis and tsunamis being caused by earthquakes. So a tsunami is a very large ocean wave that is created when a subsea fault ruptures upward, displacing enormous amounts of water in all directions. This creates a ripple in the pond effect. So when you have a fault, when these two portions kind of break free, you have this toe here shoving into the water system very quickly, and it shifts that water instantaneously. And as it does it, it creates these large energy waves throughout the water. So these energy waves travel at speeds of up to 500 miles per hour in the open ocean, but they slow down due to friction with the seafloor close to land. So they have higher speeds and energy out near the epicenter. As they get close to land, they start to interact with the sea bottom more, and there's increased friction. In the open ocean, tsunamis go unnoticed because of the depth of the ocean floor, so they're not having that interaction with the ocean floor, they're not having that friction impacting them. But as the shallow depths are approached, the wave physics start to change, and we'll discuss that in a later chapter. But as the physics start to change, the waves actually start to override itself, and tsunamis actually increase in height of tens to 100 feet in the air. And this extremely high wall of water surge can actually flood several kilometers inland because of all the energy and the height and the water contained within this wave. I'll post a link to this video. This is the earthquake that occurred in Japan in March 11, 2011. This was the fourth largest earthquake on record. There were approximately 16,000 deaths, primarily due to the tsunami that occurred. So this was a magnitude 9 earthquake that occurred off of Japan. No, it's not moving away. And that earthquake caused a ripple effect. My husband was actually stationed in Thailand at the time, and Bangkok was under a tsunami watch when this happened. So that's pretty nerve-wracking to wonder if one of those waves is going to get through these areas. They ended up not getting as sizable a tsunami as they expected. But as a geologist and or science person, this was interesting and slightly terrifying to watch. This is the Indonesian earthquake of 2004. The tsunami that resulted from this earthquake killed 230,000 people over 14 countries around the Indian Ocean. So you have your epicenter right here, and then you've got the energy radiating out from that, causing all these waves going up. Primarily Middle East, India, the Philippines. Another hazard are landslides. So similar to the soil liquefaction, the earthquake can negatively impact hill slope stability, loosening material, causing these massive landslides that can be even more damaging than the actual earthquake. This was a China earthquake landslide that killed 1,200 people. That's these two images. So earthquake belts and plate boundaries. Most large earthquakes are associated with convergent plate boundaries and transform fault boundaries in select areas. There are two major areas of earthquake activity, and they're the Circum-Pacific Belt, which is ocean plate, continental plate subduction, and ocean plate subduction. In addition, there are transform fault movements on continents, such as the San Andreas Fault. The second are the Alpine Himalayan Belt. These are continent-to-continent collisions, some ocean-to-continent subduction, and transform fault movement on the continents. So why don't divergent plate boundaries produce strong earthquakes? And this is because divergent plate boundaries, you're having new material created and slowly spreading and pushing apart the old material. You don't have that buildup of energy due to friction. You still have some earthquakes, but it's mostly as the sections of those divergent boundaries kind of slip past one another. But they're not very deep. There's not a whole lot of energy built up, so you don't get very strong earthquakes at these locations. So here's your Circum-Pacific Belt, and then here's your Alpine Himalayan Belt. And this is just the distribution of earthquakes with a magnitude of greater than 7.5, as recorded since 1900. This is looking at interplate seismicity, because we can still get faults and earthquakes within a plate system. They're not only due to plate tectonics. So here we're looking at the highest hazard to the lowest hazard. The white area is the lowest hazard. These purple or magenta are the highest. when I was living in Oxford, Ohio, I was finishing up my last year of my undergrad in geology, and it's in southwestern Ohio, right near Indiana. And there was one night I lived in a brick townhouse, and I'm lying in bed at like 3 o'clock in the morning, and it felt like my room started shaking. And I'm thinking I'd just been up way too late, and I was getting vertigo or something from trying to pull an all-nighter on studying because it was finals week. And it turns out that there was an earthquake in Illinois over right in this orange section that we felt all the way out in Ohio. So there are areas within the U.S. that are more earthquake prone, and they can have a significant impact, a couple states away. I also felt one about 5 years ago down in Harrisburg, Pennsylvania, and that was one in Virginia right in this yellow zone that occurred. So this is just a look at earthquakes with a magnitude of greater than 3 since 1974 in the U.S. So you can see there's a cluster of them here in Virginia. There's a significant group in Illinois, Missouri, Arkansas. You can see a couple very minor earthquakes outside the Buffalo area, none in the Jamestown region, and the size of the dot tells you the magnitude here. So what causes intraplate seismicity? Typically movement along the real foot rift system. So this is a supposed rift system that exists within the actual continental plate. It's not an actual full rifting apart, but there is some interplate movement and breaking up going on. So this is showing you just the area of the largest movement along that system. And we're able to use this to predict the intensity for future earthquakes of the same area. So we know that we typically get earthquakes of a 9 or an 8 in certain areas. So we know that if or when an earthquake occurs in that region again, that's about what we can expect. In Charleston, South Carolina, there was an earthquake in 1886. It was a magnitude of 7 and a Mercalli intensity of 10. 60 people were killed in this earthquake. Here's one located between Massena, New York, and Cornwall, Ontario, Canada, in the St. Lawrence River Valley. This was a magnitude of 5.8, a modified Mercalli intensity of 8. And this is actually the largest earthquake that has occurred in New York to date. So the largest earthquake that occurred in New York was in 1944, and it was a magnitude 5.8, which are, not any sort of significant structural damage or loss of life. So here's a seismicity map from 73 to 2012 in New York. So you can see it's fairly stable, very quiet. There's not a whole lot going on, especially not in Western New York. A little bit in, this northeastern section. So that's it for earthquakes. I will get those links to those videos posted for everyone. Your homework is going to cover last week, so mountain building and internal deformation. And then this week, your earthquakes. Don't forget to do your discussion groups. And I will talk to you all later. Thanks.